This is Chapter 6, Ionic and Molecular Compounds. And in this final section, Section 9, we're going to be talking about intermolecular forces in compounds. This is showing an example of one kind of intermolecular force, a hydrogen bond between two molecules of water. So the intermolecular forces that we're talking about are forces that hold two molecules together or cause two molecules to be attracted to one another. So the bonds are the forces within a molecule that hold the atoms together, right? And so this is one molecule of water here, and this is a separate molecule of water here, right? And the bonds hold the atoms together within the molecule, but then you have attractions between molecules. And those attractions are the intermolecular forces. The one depicted here is hydrogen bond, but there are others that we're going to learn about. So the first type of intermolecular force is the dipole-dipole attraction. Okay? And this comes from just an electromagnetic interaction between two dipoles, right? We learned that the dipole is, again, this sort of idealized physical model of a positive charge attached to a negative charge. But this can be realized in part in a molecule that's polar, where you have a partially negative charge on one side and a partially positive charge on the other. And so if one dipole comes into contact or comes near another dipole, the positive side of one is going to be attracted to the negative side of the other. And so they're going to align in a certain way. If you have them come side by side, right? So you have a positive and a negative. You might have them come side by side, in which case the negative will line up with the positive and the positive with the negative, and you'll get this. And so there'll be a sort of a cooperative sticking together of those two dipoles. So you can see that the dipoles, even though you have a positive and a negative, and from a distance it seems neutral, the dipoles do have a tendency to stick together to attract one another. And so this is what we call a dipole-dipole attraction between two polar molecules. Okay, so they have to be polar molecules. We're talking here about molecules, so clearly we're dealing with covalent compounds. And then there's one particular case of the dipole-dipole interaction, which is called the hydrogen bond. Okay, we saw it on the previous slide, in the intro slide for water. Here it is for ammonia. Okay, with ammonia, you have nitrogen attached to three hydrogens. But the way the shape works out, the nitrogen is at the tip of the pyramid and it pulls electron density towards itself and becomes partially negative. And that leaves a partial positive charge in all of the hydrogens. Okay, so this is a polar molecule where one side has a polar hydrogen, okay, or a positive hydrogen, I should say. And that hydrogen can be attracted to the partially negative charge on another copy of the molecule, and the nitrogen on another ammonia molecule. And so this interaction is particularly strong when you're talking about it being between a hydrogen atom and another molecule. And so this gets a special name called a hydrogen bond. Okay, it's important to keep in mind that this hydrogen bond is not the same as a traditional bond. We've been learning about all sorts of bonds within molecules. This is not a bond in that sense. It's just an interaction that's sort of strong enough that it's traditionally been given this name, but it's not a bond. So for instance, in a molecule of methane, CH4, where you have this tetrahedral structure, remember, okay, and four hydrogens attached to the central carbon, you have four hydrogens here, and these are four bonds between carbon and hydrogen, but these are not hydrogen bonds. Okay, these are not what we mean when we say hydrogen bonds. Okay, we can talk about these, and we can usually say that they're carbon-hydrogen bonds if we want to be specific about them, but they are not hydrogen bonds. And in fact, even if this molecule would encounter another molecule of methane, okay, it's still not going to hydrogen bond. So even though you have hydrogens here, there's no corresponding partially negative on another molecule, right? This carbon-hydrogen bond is nonpolar. And so there's no buildup of charge like you need for a hydrogen bond to occur. So a methane molecule is not going to hydrogen bond to another methane molecule. Even though there are plenty of hydrogens in the shape and the structure, it does not undergo hydrogen bonding. Okay, so there's two of those things to worry about or to keep in mind. The hydrogen bond is an intermolecular force. It's not talking about the bond within a molecule, and it only occurs when you have a partially positive hydrogen because that's attached to a more electronegative molecule, such as nitrogen or oxygen. The next kind of intermolecular force is the dispersion force, okay? And this occurs between nonpolar molecules. It's a very weak interaction, a weak attraction between two nonpolar molecules. It's caused by temporary or transient dipoles that are induced in the electron cloud, right? So a molecule consists of a nucleus, or really several nuclei usually, because we're talking about a couple of atoms, at least a couple of atoms together in a molecule. And they have this sort of diffuse electron cloud around them. But the positive charge of the nuclei in one molecule can attract the electron cloud from another molecule, and that's going to cause that other electron cloud to distort and pull towards it, and it's going to cause this overall interaction. It's going to cause them both to have a temporary dipole, because once they get distorted, the positive nuclei get left behind and the negative electrons travel to one side, and then another molecule will sort of have the opposite, right, where the positive is on one side, the negative is on the other side, and so you end up with this weak interaction between the temporary dipoles, and then the temporary dipoles will dissipate because the molecule sort of bounces back and then moves on to another molecule and maybe then forms another temporary dipole. So it's similar to dipole-dipole interactions, but because it only occurs temporarily, it's very weak. Okay, and so this is the only force that really holds together nonpolar molecules into the liquid or solid states. Okay, if it weren't for these transient dispersion forces, the molecules in a nonpolar compound would not be attracted to one another at all. They would constantly just bounce off one another and go their separate ways, and they would always therefore be in the gaseous phase. Okay, in order for molecules to condense into the liquid or solid phase, there has to be some attraction between them, some stickiness holding them together. And so this brings us to the melting point, right? Melting point or boiling point. These things depend on the intermolecular forces of a compound. So the stronger the intermolecular forces, the higher the melting points and boiling points, right? If the forces are stronger, it means the molecules are sticking together more, and you have to put more energy into them to break them apart. Okay, so if you have only weak forces like dispersion forces, then your compound is going to have a very low melting or boiling point. If they're higher, it's going to have a higher melting or boiling point. So hydrogen bonding is even higher, and that'll give you a higher melting point, for instance, in water. Okay, and then the last type we can think about are not technically really the same intermolecular forces, but ionic forces are also along the spectrum. And ionic forces or ionic bonds between ions within a compound, within an ionic compound, are the strongest. They're much stronger than the intermolecular forces, and they're even usually stronger than covalent. So this chart summarizes that, right? You have the dispersion forces here at the bottom. These are the weakest. Then the dipole-dipole interactions, which are a little bit stronger. The hydrogen bonding, which is a particularly strong example of a dipole-dipole interaction. And these are all forces between molecules. In other words, these are all intermolecular forces. Okay, and then more strong than intermolecular forces are the forces between atoms or ions, and these are what we really call bonds. Okay, so again, hydrogen bonding, even though it has that name, it's not really a bond, it's an intermolecular force. The bonds that we talk about are covalent bonds and ionic bonds, and ionic bonds tend to be stronger than covalent bonds. Okay, that's not uniformly true. There are some covalent bonds that are stronger than some ionic bonds, but generally the range of strengths for ionic bonds is higher. And in addition, with ionic bonds, you typically have a large number of ions, and the bonds between them are all sort of working together. So they're all holding these ions into a very rigid crystal structure where there's multiple bonds to neighboring ions. Okay? With covalent bonds, you typically just have a bond between two atoms, and that's part of a molecule, but it doesn't. They don't necessarily all cooperate. And so this table shows you how that's reflected in the melting points, right? You have the ionic compounds with ionic bonds, and that has the highest melting points, right, by far. Then the next set is the next strongest intermolecular forces, which are really hydrogen bonds. Okay, so water and ammonia undergo hydrogen bonding, and they have pretty high melting points, relatively speaking. The next set is dipole-dipole, and those are a little bit lower. And then finally dispersion forces, which are a little bit lower than that. Now you can see it's not uniform, right? Not every dipole-dipole attraction is lower than every hydrogen bond, because there are other factors involved. The size of the molecule is important to the size of the atoms within the molecule, or the type of bonds between them, and things like that. There are other factors, but in general, this is why nonpolar molecules tend to have lower melting points than polar molecules, and hydrogen bonding molecules have even higher melting points. This is an example of the kind of question you might be asked about intermolecular forces. We generally keep it pretty simple, but for this you have a list of different compounds and you want to identify the main type of intermolecular force in each compound, right? The main type. And so what that means is the strongest kind of interaction, the strongest kind of intermolecular interaction. In general, molecules would tend to experience many different types, right? So if a molecule is polar, it'll have dipole-dipole interactions, but it can also have some weak dispersion forces because its electron cloud is still, polarizable and squishy in a sense. But those dispersion forces will be weak compared to the dipole-dipole interactions, and so we ignore them. So when we want to know the intermolecular forces between molecules in a compound, we're looking for the strongest one, the most important one. And so we should think about them in order of their strength and go through from the strongest to the weakest, right? So first we consider whether the compound has ionic bonds, and then if it does, that's your answer. If not, then we think about whether it can undergo hydrogen bonding. If it can't do hydrogen bonds, then we think about whether it's polar in general. And if it's not polar at all, then we have to fall back and say that it must have only dispersion forces between the molecules. Okay, so you go through them sort of in order. Some of these we'll need to look at the structure, some of them we might not need to, so let's just go through them. The first is NCl3. Okay, so with NCl3, you have a bunch of polar bonds. Chlorine is more electronegative than nitrogen. Okay, so you should think about the shape, because once you know you have polar bonds, you have to worry about whether they cancel out or not. In NCl3, this is a trigonal pyramidal structure, and so they don't cancel out. You have three polar bonds that are all pulling down on the nitrogen at the apex of this. Remember, this is sort of a pyramid. These chlorines are at the base, and the nitrogen is at the peak. And so these are all pulling down on this, and so this overall has a downward pointing dipole for the molecule overall. Okay, so it doesn't do ionic bonds, right? This is not an ionic compound, so we don't have to worry about ionic bonds. There's no hydrogens anywhere in the molecule, so clearly it can't do hydrogen bonding. But we see that it is polar due to its shape and the polarity of the bonds, and so it can undergo dipole-dipole forces. Okay, so the answer for NCl3 is dipole-dipole. Okay. The next one is water, H2O. Okay, water is a covalent compound, so we don't have to worry about ionic bonds, right? It's clearly not going to undergo ionic bonding. But hydrogen bonds, well, maybe it has hydrogens in it, so we have to take a look at the structure and see if it might be able to undergo hydrogen bonding. Water, I highly recommend you just memorize the Lewis structure for water, and not just the Lewis structure, but this particular way of drawing it, which shows that it has this bent shape. Okay, that's very important for the properties of water, is to remember that it's bent. Okay, so since water is bent, it has these polar bonds where the oxygen is pulling on the electrons more strongly than the hydrogens, and so those are pushing it in, and that gives this an overall polarity, where you have a negative charge on top, and the hydrogens are positive, right? Partially positive. So what that means is you have hydrogens that are attached to a very electronegative element and therefore becoming partially positive. And so that is going to allow this to undergo hydrogen bonding with another copy of the molecule, with the oxygen in another water molecule. And so this is hydrogen bonding. So the answer for B with water is water can hydrogen bond. Okay, and that is important for the properties of water. It gives water a lot of its properties, like its melting point, boiling point, surface tension, things like that. Okay, the next one is BR. right? So BR-BR really is talking about a Br2 or bromine molecule. You have two bromine atoms attached together. They have a bunch of lone pairs, but that doesn't really matter because it's just one single bond in the molecule. And this is a nonpolar bond, right? The two elements are the same, and so this is a completely nonpolar bond, okay? So it's not ionic, can't undergo ionic bonding. Clearly there's no hydrogen, so it can't do hydrogen bonding. It's nonpolar, so it's not even going to do dipole-dipole forces, so that means the only option left is that it must have dispersion forces. Okay? So the only thing keeping one molecule of bromine stuck to another in the liquid phase are the dispersion forces, the temporary dipoles between them. Okay? The next one is KCl. Okay? And this is very easy because we start at the beginning, ionic bonds, and we see that K is potassium, that's a metal, which means this must be an ionic compound, which means the strongest forces here are going to be the ionic bonds between the ions. Okay? And then we're done. Now, we don't have to worry about hydrogen bonds or dipole-dipole or dispersion forces or any of that, but it is important to keep in mind that KCl is sort of the most extreme example of a polar molecule. It's not really a molecule because we talk about networks of lattices of ions in an ionic compound, but again, it's a very polar compound. Pretty much all ionic compounds are very, very polar. And then the last example is NH3, and we've seen this a couple of times. It's not ionic, so it's not going to undergo ionic bonding, but NH3 was one example that was given for a molecule that can undergo hydrogen bonding, right? The nitrogen side is going to be partially negative. The hydrogens are all going to be partially positive. And so those are going to be able to hydrogen bond to the nitrogen in another ammonia molecule. Okay, so you're going to get hydrogen bonding between them. And so for ammonia, you also have hydrogen bonds. Okay, and so these are your answers. This is a chart just outlining the topics that we learned in Chapter 6. The first part was ionic compounds, and so that encompasses all this stuff, right? Ionic compounds, understanding ionic bonds, how the bonds form through the transfer of electrons to satisfy the octet rule, how metals form positive ions, nonmetals form negative ions. Along with positive ions, you also have ammonium. All right, and along with the negative ions, you have a whole list of a bunch of polyatomic ions, right? Those positive and negative ions will come together to balance their charge to form a neutral compound, and that helps you to write the chemical formula and the chemical name for the compound. So all this stuff are things that you need to remember for ionic compounds. For molecular compounds, we have the concept of covalent bonds, how covalent bonds work, the fact that these are between nonmetals, that the bonds can be polar or nonpolar, how to draw Lewis structures to indicate the shape of a molecule, and how we can use VSEPR theory to figure out the shape, and then the shape and the bond polarity and electronegativity to figure out the molecular polarity. Okay, so remember, bond polarity and molecular polarity are related, but they're different concepts. And then we also have the intermolecular forces within a molecular compound, which are again a result of the shape and the polarity. Okay, and so you can remember those 4 different types of intermolecular forces. And so these are all the things that you need to know for the covalent compounds. And together, this is Chapter 6.